I also thank you for IEEE Sensor Organizer for giving me the opportunity to present our work, a fully integrated refractometric sensor in silicon nitride. And my goal today is to present the integrated spectrometer design. I'm Asih Syahadi, PhD student from Université de Toulouse, and collaborate with LAAS-CNRS France. Here's my contents of my presentation today. For the first, I start with an overview of the optical sensor and then explain the integrated spectrometer. Next, I discuss about the scanning scheme and and then I will show the measurement setup and the experimental result. And finally, I summarize my presentation in conclusion. I will give a brief an overview of the optical sensor. That we know the optical sensor works by converting the measured or physical parameters into a measurable optical signal by using the measurements induced to a change in optical properties of the sensor materials. For the instance, the refractometric sensor is a type of optical sensor that focuses change in refractive index of the medium or the waveguide itself and leads to an optical response change. In here, there are several types of the sensing mechanism: intensity-based, polarization-based, scattering-based, and wavelength-based. And we are specifically utilizing the wavelength-based sensing approach, and it's implemented to the integrated photonics. To measure, next question, how to measure the wavelength output of the optical sensor? Usually we require the conventional spectrometer. However, the conventional spectrometer is often bulky, expensive, and incompatible with the modern photonic structure. So in here, we developed the integrated spectrometer. By designing the integrated spectrometer, we can combine the optical sensor and spectrometer into a single chip. And there are two most widely used for the photonics, integrated photonics platform. The first is the silicon platform, and the second is the silicon nitride platform. In our work, we use the silicon nitride platform because it has broadband width of spanning from the visible to near infrared, and it allows for diverse range of the applications. However, the silicon nitride platform has a lower index contrast that consequently needed the larger band radius to minimize the optical loss. Now I will discuss about the silicon integrated spectrometer. There are two types of integrated spectrometer based on the fundamental technology route. The first is the wavelength multiplexing that split the incident signal of spectra and measure the intensity of the individual channel. And the second is the wavelength multiplexing that do not require for splitting the incident signal spectra. In this work, we use the wavelength multiplexing spectrometer types. And following the approach of this reference, the authors designed the silicon integrated spectrometer with a two-stage system. The primary stage is a high resolution tunable filter by using the at-drop microring resonator. And we can see the spectrum of at-drop microring resonator provides a high quality factor correspond to the high resolution. And it has a periodic transmission spectrum with a limited of the FSR correspond to the narrow bandwidth. So in here, they require for the secondary states to provide the wider bandwidth. They use array waveguide grating for the secondary states. And this is the array waveguide grating bandwidth that corresponds to the optical bandwidth of the spectrometer. And then implement the heater, micro heater, electric heater in here for enables the resonance wavelength scanning of MRR across a fully FSR. And we can see by combining the both structures, we can obtain a high resolution and wide bandwidth integrated spectrometer. And this is the silicon nitride spectrometer specification of this paper. And this is our silicon nitride integrated spectrometer specifications. Now, I will talk about the proposed silicon nitride integrated spectrometer. Consists of two stages. I start from the secondary stage that we use array waveguide grating, and the output channels of the array waveguide grating are connected to the photodiode. In this structure, we use a 5 output channels, and if the bandwidth specification is 50 nanometer, so the channel spacing is 10 nanometer. So the channel spacing must match with the FSR of the MRR. Now we have the specification of the primary state that the FSR is 10 nanometer and the resolution is 0.2 nanometer associated to the Q factor larger than 8K. So if we implement the 8-drop micro resonator, we can calculate the ring radius is 19 micrometer. As I mentioned before, that the silicon nitride has a low index contrast. So the minimum bending radius to contain the losses at least 50 micrometer. So in here, we propose the Fechnier method to keep the high FSR 10 nanometer and the ring radius larger than 50 micrometer. So this is the proposed PIC, our PIC that consists of the plasmonics biosensor for the sensing element and the integrated spectrometer for the measurement device. And for the primary state, so we applied the Fechnier function by cascading the 2 microring resonators. We call the cascaded microring resonator, and we can calculate the FSR of CMRR by using the Fechnier principle. And then for the secondary states, we used the array waveguide grating, has 5 output waveguide channels and 1 output waveguide channel associated to 1 wavelength information. We already defined the M15 and M23 based on the previous slide, and we can calculate the FSR 1, 2 nanometer, and FSR 2, 3.3 nanometer. And we can see that the ring 1 and ring 2 are larger than 50 micrometer. So this illustration to explain the working principle of the CMRR, we have at drop micro resonator 1, and the FSR is 2 nanometer, and we have a drop micro resonator 2, and then the FSR is 3.33 nanometer. By cascading the MR1 and MR2, we can obtain the spectrum, the CMRR spectrum with the FSR 10 nanometer. And now we talk about the scanning scheme. For the first scanning scheme is the temperature scanning for FSR 10 nanometer. This is the illustration of the temperature scanning. We scan for the first resonance wavelength for 10 nanometer. Then return to the initial position. And by using this equation, we can calculate the delta NF 0.0129. And because the thermo-optic coefficient of silicon nitride is very small, it requires a high temperature variation above 500 Celsius degree. So we developed another scheme to replace the temperature scanning for FSR 10 nanometer using the smallest FSR in here is 2 nanometer. So, and the delta NF is the 0.00258. So if we scan for 10 nanometer, it means the scanning ring is 10 nanometer, and the scanning step is 2 nanometer. So we need to scan 5 resonance wavelengths of the micro resonator 1. For the first scanning, we have to scan the we have to scan the lambda 11 and lambda 21, scan together for 2 nanometer. And then we scan for the lambda 212, means the second resonance wavelength of the microresonator 1. And before we scan together with the lambda 22, we have to adjust the lambda 22 aligned with the lambda 12. So we scan together for 2 nanometer. And this process are repeated for lambda 1, 3, 1, 4, and 1, 5. Okay. So by using this scheme, the delta T is 100 degree. It's 5 times smaller than the previous scheme. And for the MR2, the delta T is 175 degree because the FSR is 3.33. Now the measurement setup, we use a silicon nitride materials for the waveguide materials. And then we measure the CMRR and AWG separately. And this is the measurement setup for our chip. And this is the fiber array configuration. Now we discuss about the preliminary result of the CMRR. Based on this spectrum, based on this spectrum, the FSR is 11 nanometer. It's slightly higher than the design of FSR. And then the full width at half max is 0.22 nanometer. Is correspond to the resolution of the CMRR. And now we talk about the array waveguide grating measurement result. And we have 5 output waveguide channels, and the channel spacing close to 10 nanometer, and the AWG bandwidth is close to 50 nanometer. And the adjacent crosstalk is minus 18 dB. Now we are in the conclusion, and we have a design, fabricate, and characterize the AWG and the CMRR. But in here, we need optimize the FSR of the CMRR. And for another result is the experimental result match with the target specification. And for the obstacle is we have a complex temperature scanning for CMRR because we need to synchronize between the spectrum of the MR1 and MR2. And for the next step, we implement the thermo-optic scanning by using the microheater, and also implement the electro-optic scanning by using the electro-optic polymer as the cladding. And we design a fully integrated spectrometer by combining the CMRR and AWG. This is the reference for this paper, and thank you very much for your attention.